In this video, I'm going to conclude our discussion on quantum scattering theory. And so in this one, we will be using the Born approximation method to calculate the scattering of a, a particle, which is a wave as well, off of some potential. And so in the previous video, we did a lot of math type stuff in order to go from the differential form of the Schrodinger equation to the integral form of the Schrodinger equation, which is this. And so with this, we have the wave function on both sides of the equal sign. So that's what I have in green. And so those are the same function, which means that we would have to know something about the solution in order to find the solution. But if we want an exact solution, then we need to do something else. We need to use what is called the Born approximation method. And so we have our potential V here centered around the point R sub naught, and we want to calculate the wave function at points far away from the center of that potential, so that means that our R is much greater than our R sub naught here for all points in this equation right here. And so we have our R minus R sub naught, so the difference between those squared, which would kind of look like this here. So it's kind of like the Pythagorean theorem. And then we can set that equal to R squared plus R naught sub squared. So if we just factor this out, then minus 2 R dot R sub naught. But because we are looking at where this is much bigger than the R sub naught, then we can ignore this R sub naught term because that's going to be extremely small, and then we're squaring it, so it's going to be even smaller yet. And so we can make this approximation right here. So we take the square root of both sides to get this. We use the binomial expansion to get it in this form here, since the higher order terms on here will be very small because of this R sub naught term here. Then we distribute this R into it and end up with this, and then this the R vector here divided by R just gives us the R hat here, which is just sort of the R direction. So it's just the sort of basis vector in the R direction. And so what we end up with is this right here, where R minus R sub naught is equal to this R minus the component of R sub naught here in the R direction. So then we can make some substitutions here for our k. So we have the k prime vector here is equal to the component of k in the z direction. Then this k right here is equal to the component of k in the r direction, which means that we have this here. So this e to the I k r minus r sub naught is approximately equal to this e to the I k r times e to the minus I k dot r sub naught right here. And so remember, this is what we will have here in our integral form of the Schrodinger equation. So we take this blue thing that we got and this red thing that we got, and then we put it into our Schrodinger equation right here. But once again, our R is much greater than the R sub naught, so we can sort of cancel that out, and we end up with just the R in here. Then we just kind of shift some things around to get it in this form, where what we have right here is a spherical wave, and it's not dependent on this R sub naught. So recall that our incident wave is equal to this A times e to the ikz, which means that we can put that in for this wave function right here. So we put that in right there. And we have this outside the integral. So we could pull that outside the integral because, like I said, it's not dependent on this R sub naught right here. So we can pull it outside the integral. But this right here is a spherical wave multiplied by a constant. And so we can put it like this, which then gives us this for our Schrodinger equation right here, where we have the incident wave right here, we have the scattered wave times this A times this integral right here. Well, we can just say that that integral right there is our scattering factor right here, this f of theta. And so we can put it in this form right here. So that means that this is our f of theta and phi right here. So this is the equation that we get here, the Schrodinger equation that we get right here. So the Born approximation assumes weak scattering, and so the incident wave is not significantly altered by the potential. And so this this phi, or this psi rather, right here of r sub naught is approximately equal to this psi of 0, which was our incident wave. And so using this this that we did, so this k prime is equal to the k in the z direction, we get this right here. So this is our psi right here, which is equal to this incident wave right here, which we are now setting equal to this a times e to the I k prime dot r sub naught right here. And so we get, when we put that into our integral here, we end up with this for our scattering factor. So we're replacing this psi of r sub naught right here. And so for low energy, we have that this right here is about equal to 0. So I guess it helps to sort of know what this actually means. So if you've kind of forgotten, so this k prime is is in the z direction here, so that's the incident wave, and this k is the wave factor for the scattered wave, and so this theta right here is the angle between the incident and the scattered wave right here. And these k prime and k are the wave numbers for both of those waves. And so when we have this equal to 0, this right here will go to 1. And so we have this right here. And this is the scattering factor from the Born approximation at low energy here. For higher energy, this will not be equal to 0, and in fact it'll be equal to this kappa here, which is this right here, dot r sub naught times cosine of theta. And so this means that our z-axis, or the polar axis, r sub 0, is lying along kappa. So this gives us a scattering factor that looks like this. So we have this kappa dot r sub naught cosine up here in the exponent right there. Since the scattering potential is spherically symmetrical, then it's only a function of theta, so we can sort of integrate out this phi here, which will just end up being 2 pi, so that ends up giving us this, well, it would give us 2 pi in the numerator, so that would just sort of cancel out that 2 pi right there. And so we end up with this integral right here, where the kappa is equal to 2k times sine of theta over 2. And so that is right here, and that is what gives us the angular dependence of the f of theta here. All right, and so these scattering factors, these are telling us how much something scatters. And so in classical physics, that is similar to what we have here for this, what's called the transverse impulse. So it's given by this force here acting transverse to the path. So we see that it's moving this way, where the particle's momentum was that way. And so it is acting transverse to the path of the particle for some amount of time. And so we integrate that over time. And so what we would get for the angle then is theta is equal to the inverse tangent of our impulse over the momentum that it had in the incident direction here. So this is a first order impulse approximation. So the 0th order would be no deflection at all. And so remember, we said above that our sort of 0th order Born approximation was that the incident wave is not significantly changed. And then at our first order approximation, we ended up getting some amount of change. So that was this f of theta right here. So there's some amount of change because it is dependent on this angle theta here. All right, so like I was saying, similarly, the 0th order Born approximation has no effect on the incident plane wave, and so that was this right here. And then we see that this doesn't have any dependence on theta here, but the first order was this, which the kappa carried our theta dependence there. And so that's the 0th order approximation and first order approximation for the Born approximation. So these came from the integral form of the Schrodinger equation, which remember we had our Green's function here, which is in our integral right there, where this is the incident wave. So schematically, this looks kind of like this, because we have this Green's function here, we have this potential term right here, and then we have our psi right here. So that is the that is the incident wave right there. Or no, that's not the incident wave, because the incident wave is sub-zero right there. So this is just the same function as this right here. And so it has sort of schematically this form. But if we plug in this psi equals this into this psi right here, we end up with this. We sort of distribute the integral into these square brackets here, so we end up with this right here. And if we did that again, we'd have this right here. You could keep iterating this to higher and higher orders. So we have the 0th order, the first order, second order, third order Born approximations. And this is called the Born series right here. And so we keep getting higher order terms, which give more and more complicated interactions with these scattering potentials. So this is our 0th order term right here. Then we are sort of adding on this first order term here, which has a single v and a single g, like we have up here. Then we add this one here, which has 2 V's and 2 G's here, which this has right here. And then we keep adding more and more. So we'd even add more after that. So you could keep adding more and more terms to it to get a more and more accurate sort of description of the way that this particle is interacting with the potential. And so if you are somewhat familiar with like quantum field theory or quantum electrodynamics, you'll see that these are similar to Feynman diagrams, where the higher order terms are being sort of more complex interactions, where in Feynman diagrams, so you can have particles coming in like this, and they exchange a photon like that, or you can have them coming in like this and exchanging 2 photons here. And so you can get these higher order terms in your Feynman diagrams. And so the other thing to note is that we can see that this g here, which is our Green's function, is a response to some interaction with the scattering potential v. So like this g here was a response of sort of shifting by some angle here. So we're looking at some angle theta here, to the incident path right there. And so that's some response to it. Where this one over here then has these 2g terms here, which means that we have sort of 2 different responses. So this we'd have a response there, but then we have this going right there, so we have another response right there. So another response going on right there. And so you can keep adding these higher order terms. And that's why we can also think of these interactions happening at these vertices here as being somewhat low energy, because when you're adding a bunch of these low energy terms together, that ends up sort of including all of the sort of energy that would actually occur in the interaction. But anyway, I don't want to ramble on too long with this. That, like I said, was the Born approximation method for quantum scattering. But anyway, I hope you found this video helpful, and I will see you in the next one.